Welcome to On Chemistry. In this video, we are going to see important rearrangement reaction, which is Beckmann Rearrangement reaction. We studied in more detailed way with 22 fully solved examples. Stay tuned. What is inside this video? Basically, we will see what is Beckmann rearrangement, then mechanism, then basics. Basics include migrating ability, how anti-group migrates, that is stereospecificity, and Beckmann elimination. It is also called as fragmentation. More importantly, we will see 22 fully solved examples from various examinations. This is very important and it will be very helpful to you. At first, we will see basics of Beckmann rearrangement. This all the things will help you to understand what is rearrangement, why it is important, and how it is used for synthesis. All the basics you will learn in the first section. The first obvious question will be, what is Beckmann rearrangement? It is basically a conversion of oxime into amide. You are using acid as the catalyst, one group migrate that create mechanistic pathway to amide. You can use acid. Acid can be Lewis acid or Bronsted acid. And the fact here is trans group migrates. That's why it is stereospecific. And if stereochemistry is not mentioned, you can migrate the more electron richer group because there is a chances of cation formation. So if stereochemistry is not mentioned, means migrating ability hydrogen is high, then phenyl, then tertiary, then secondary, then primary. Now we will see mechanism, how oxime converted into amide. You are using the acid, oxime has OH group, so OH convert into water, ready to leave because water is the leaving group. The leaving can be assisted by the migration, methyl migrates, H2O removed and cation form. Since methyl is moved, valency is deficient, so it forms cation. Then OH attacks, you have OH, there is a enol there, so heto-enol tautomerism possible, end up with amide, OH converted into ketone there. There is some argument over the mechanism, whether the intermediate is cation or not. It can be concerted, may not be concerted, but our interest is to find the final product. Don't debate on the mechanism. There is always debate on intermediate in every mechanism. There is supporting evidence for all of this. So just go with your understanding, find the final product, don't debate on cation. Let us see very important thing, which group migrates during the rearrangement. Here I given two same compound, only differ in the stereochemistry. In category 1, stereochemistry specified, category 2, stereochemistry not specified. In first category, stereochemistry specified means trans group migrate. If stereochemistry not specified means electron rich group migrates. Why? Because intermediate is the cation. That's why electron rich group migrates. We will see very detail each category. The first category is stereochemistry specified. Here I given same compound with different stereochemistry. One is pH is trans to OH, another is CH3 is trans to OH. Only differ in the stereochemistry and position. The migrating ability will be trans 1 since stereochemistry is specified. In first case phenyl migrate, second case methyl migrates. So what you should learn is if stereochemistry is specified means trans group migrates. In the next category, stereochemistry is not specified. Here phenyl and methyl is there. We don't know which is cis or trans. How we can do the mechanism means choose the electron rich group. Since the intermediate is the cation, electron rich group migrate, which is phenyl here, migrate, end up with the final product. The migrating order will be hydrogen, phenyl, tertiary, secondary and primary. Why this order means intermediate is the cation. So electron rich groups or cation stabilizing species migrates. Then the very important basics, migrating group with chiral carbon. What will happen to chirality? Suppose you start with S, whether it end up with S or R or racemic mixture. Here retention of configuration is happened. Here retention of configuration is happened. In this example, here I given chiral carbon. Chiral carbon is the migrating group. Since it is trans to OH, it migrates. First step, OH is protonated, water form, trans group migrates. Since trans group is the chiral carbon, it migrates, it form cation. Then OH formed by quenching, OH is formed, then it converted into ketone. The important thing you should learn here is there is no change in the configuration during the transfer of the groups. This is a very important fact because the chiral carbon not changing means the mechanism is concerted mechanism. There is on and off proof for concerted as well as non-concerted. Here it is a proof for concerted mechanism. Then the next one, Beckmann elimination. It's a kind of different direction. If there is a stable intermediate formation, then there will be a different mechanism, different pathway. Here I given simple example for quick understanding. In first step, acid attacks, OH become OH2. Then hydrogen migrates. You have cation formation. The cation has to be quenched. Since the carbon is very stable, cation quenched the cyanide, not the amide or different pathway. So the pathway is different, mechanism is shortened, you get cyanide instead of amide. There is a different quenching mechanism here. The reaction also called as Beckmann elimination or Beckmann fragmentation. Whenever you have stable intermediate, you always think of elimination reaction. Then short note on starting material. Always starting material need not to be oxime. It can be ketone converted into oxime. So whenever you see multi-step, you always consider ketone can be involved in the Beckmann rearrangement through the oxime formation. You have to do extra one step for the conversion. Ketone, oxime, then rearrangement to amide. Then we are getting into very important thing, 20 fully solved examples from various examination. Why so many? Because problems are best way to learn. It will give different perspective. It will also kind of revising mechanism. It help you to learn the concept in terms of problem solving. Let us see the first example, cyclohexanone. First step you are using oxime, then sulfuric acid. You should find what will be the final product. Here you are having ketone, oxime you are using. First step conversion of ketone into oxime, then you are using the acid. So possibility of Beckmann rearrangement. First step will be attack of acid on OH. So H2O remove. The H2O is assisted by the trans group, which is the ring carbon, which is methylene group. It migrates. You have cation near the new carbon there. Here the ring is expanded. If you redraw nicely, you have 7-member ring. That is 6-member ring becomes 7-member ring. Cation has to be caught. So OH minus from the water attacks, you have OH formation. Here you have enol structure. So enol can be converted into ketone. So ketoenol tautomerism occur, end up with amide. The concept you outline here is in cyclic system, Beckmann rearrangement mostly promote the ring expansion. Then the next example, you have oxime. One side you have benzene, another side you have toluene. You are using the sulfuric acid. You should find what will be the final product. Here by looking at the oxime, you might realize it's a Beckmann rearrangement. So as it attacks the oxime, you have H2O, it's a good leaving group. The trans group is the migrating group because anti-group migrates, anti-group is toluene group. It migrates, assists the water leaving. You have cation and the benzene carbon. Then the cation has to be quenched. So OH minus from the water attacks. You have alcohol. The alcohol is enol. If you do tautomerism, it forms ketone. The concept you outline here is the migrating ability of Beckmann rearrangement. The group trans to the OH migrate. Then the next example, you have cyclobutane. It has 1,3-diketone. You are treating with hydroxylamine and sulfuric acid. We should find what will be the final product. Here you are having ketone. You are using the hydroxylamine. So chances of hydroxylamine formation, diketone become dihydroxylamine. Then you are using the acid. Here nice thing will happen, which is both OH protonated, both OH removed. It form dication. Then the dication has to be quant. So OH minus from water attack. You have diol there. The diol is enol. It converted into amide there. The concept you have learned here is if diketone is there, both get hydroxylamine formation, end up with multiple Beckmann rearrangement. Then the next example, you have hydroxylamine. One side it has phenyl, another side it has methyl. You are using the sulfuric acid. You should find what will be the final product. Here you are having the oxime. You are using the acid mean oxime OH become OH2, that is H2O. It is a good leaving group. The leaving group is assisted by the phenyl. Why? Because phenyl is the trans group. It migrate. It remove the OH to form the cation. Then the cation has to be quant. The OH minus attacks. You have enol. Since there is a enol, there is a possibility of hetoenol tautomerism. So enol become ketone. You end up with amide there. The concept you have to learn here is if stereochemistry is specified, trans group migrates in the Beckmann rearrangement. Then the next example. Here you have decline system. Connected carbon, you have oxime and methyl group. You are using the sulfuric acid. You should find what will be the final product. Looking at the oxime, you might realize it's a Beckmann rearrangement. As expected, acid attacks the alcohol. You have H2O formation. Then migrating group is CH3 because ring cannot move. Ring is very rigid. So only possibility is methyl because you have to quench the charges. Methyl migrate. You have cation and the carbon. Then OH minus from the water attacks. You have alcohol. The alcohol is in the enol form, so it converted into ketone by tautomerism. So finally end up with amide. The concept we outlined here is rigid ring carbon cannot move, particularly in the decline system. Hence this group can migrate to quench the charges. Then the next example. Here you have decline system with methyl and ketone. You are using hydroxylamine and sulfuric acid. You should find what will be the final product. Here you have ketone. You are using the hydroxylamine. Here hydroxylamine form away from the methyl group. Why? Because of steric reason. Methyl group is relatively bulky. Don't allow the OH formation at the same site. So what really happened? The hydroxylamine form away from the methyl group. Then protonation happened because you are using the acid. OH become OH2, ready to leave. Hence, trans group assists the reaction. You have the cation there, ring expand. So if you redraw nicely, 6 member becomes 7 member ring with cation. Then OH minus attacks. You have alcohol there. The alcohol is the enol. Through hetoenol tautomerism, it becomes ketone, that is amide there. The concept we outlined here is hydroxylamine formation is crucial if there is a steric hindrance that can promote the hydroxylamine formation. Then the next example. Here you have cyclopentanone with two methyl groups. You are using hydroxylamine and sulfuric acid. You should find what will be the final product. Here hydroxylamine is there. As usual, ketone converted into hydroxylamine. Due to the steric reason, hydroxylamine form away from the methyl group. Hence, methyl groups become trans there. Then alcohol is there. You are using the acid. So H2O elimination happened, which is assisted by the trans group. Trans group here is methylene group. So it migrates, it forms the cation. Here 5-member ring is strainful. So ring strain also help the ring opening. Ring open, you have cation at the carbon. If you redraw nicely, 5-member ring becomes 6-member. You have cation in the system. Then OH minus attacks the cation, which is from the water. It forms alcohol. Alcohol is technically a enol. Through hetoenol tautomerism, it becomes ketone. That is amide there. The concept you have to learn here is the strain also can assist the reaction, promote the Beckmann rearrangement. Here you have fused system. Two 5-member rings are fused. You are having hydroxylamine and you are using the sulfuric acid. You should find what will be the final product. Here, Beckmann possibility is there because oxime in acidic condition. First step will be OH attack on H plus, H2O removal. H2O removal assisted by the trans group because that is the migrating group which migrates. You have the cation. Since the ring is 5-member, it is strainful. Hence, ring strain also assists the reaction to relieve the strain. So 5-member becomes 6-member. You have cation in the carbon. If you redraw nicely, you have cation. OH minus attacks, it is the enol there. So enol can convert into ketone through tautomerism. You end up with final product. Actually, ring expansion happened by the formation of amide there. The concept you have to learn here is in Beckmann rearrangement, if there is any strain in the system, it can also assist the reaction, promote the Beckmann rearrangement. Then the next reaction, you have fused system, 4-member and 6-member, and the phenyl and hydrogens are synced to each other. In 4-member ring, you have oxime. You are using the sulfuric acid. You should find what will be the final product. Here you have alcohol in 4-member ring. So Beckmann rearrangement will happen quickly because of ring strain. First step will be alcohol attacks the acid. You have H2O formation. According to Beckmann rearrangement, trans group migrates. Trans group is methylene carbon. It migrates, H2O leaves by the assistance of it, and you have ring expansion. If you redraw nicely, you have the conversion of 4-member ring to 5-member ring with cation. Then OH minus from water attacks the cation. You have the enol. Then the enol converted into ketone by hetoenol tautomerism. So the final product is ring expanded amide. The concept you have to learn here is ring strain can assist the Beckmann rearrangement. Then the next example, you have pyrrole, side chain you have hydroxylamine, you are using the sulfuric acid. You should find what will be the final product. Here oxime in the side chain, so Beckmann rearrangement possibility in acidic condition is possible. You are using the acid. Acid attacked by OH form the H2O. According to Beckmann rearrangement, trans group migrates. Hence, pyrrole migrates. You have cation in the system. During the migration, H2O removal happen by the assistance. If you redraw nicely, you have cation at the side chain. It is attacked by OH minus from the water. So enol form. Enol can be converted into ketone by tautomerism. So final product is side chain amide there. The concept you outlined here is even pyrrole can be a migrating group in Beckmann rearrangement. Then the next example, here you have ketone which is in the bridged bicyclic compound. Bridge contain 2 methyl group and the bridged carbon contain 1 methyl group. You are using hydroxylamine and acid chloride. You should find what will be the final product. This example is classic example for Beckmann elimination because it can form stable cation. First step will be attack of ketone by hydroxylamine, form the oxime there. Then acid chloride you are using, which can promote the OH elimination, but OH elimination leads to the stable cation. Since the cation is the tertiary cation, it is stable, so it cannot allow any further reaction. So bicyclic system become monocyclic by the cation and side chain cyanide. So cyanide is the only quenching pathway. The cation is there. Then cation has to be quenched. It quenched by H plus elimination. You start from bicyclic compound, end with monocyclic compound. That's why the Beckmann elimination is interesting. You will get unexpected products. The concept you have to learn here is whenever you have stable cation, you have the possibility of Beckmann elimination. Then the next example. Here you have hydroxylamine. Phenol and anisole are there. You are using the sulfuric acid. You should find what will be the final product. Here you have oxime acid you are using. So chances of Beckmann rearrangement. First step, acid attacks the OH. You have H2O formation. Which group migrates is the real question. Here, trans group is phenyl, not anisole. So phenyl migrates, H2O eliminate. You have cation there. Then the cation quenched by OH minus. OH minus attacks. You have enol. Then through ketoenol tautomerism, you have amide formation. The concept you outline here is even though anisole is more electron richer than phenyl, phenyl is in trans position, hence the migration of phenyl happened. Then the next example, you have benzophenone. You are connected with hydroxylamine hydrochloride, sulfuric acid, water, bromine and ferric bromide. You should find what will be the final product. Here it is the organic conversion reaction. Many reagents are there. First step will be oxime formation because you have ketone, hydroxylamine, oxime formation. Next step is Beckmann rearrangement. Acid attacks the water. You have H2O elimination. You have H2O elimination by migration of phenyl group. Phenyl group migrates. You have cation formation. Then the cation quenched by OH minus. You have enol. Then the enol converted into amide through hetoenol tautomerism. Final product is obtained, but you have bromine and ferric bromide. Chances of aromatic electrophilic halogenation. But where the bromine attack is the interesting question. Since the bromine is the electrophile, it attacks the electron rich ring. Hence, A ring is getting attacked because nitrogen is the electron donating group because of its lone pair. Attack happen, you end up with final product. Here regioselectivity happen because of electron richness. This reaction is important because it has stereoselectivity as well as regioselectivity. Then the next example, you have benzene attached with cyclohexane. It has hydroxylamine. You are using sulfuric acid. You should find what will be the final product. Here you are having hydroxylamine. You are using the acid. Hence chances of Beckmann rearrangement. So first step, acid attacks the alcohol, make it as H2O. Then trans group is benzene carbon. It can migrate, assist the leaving of H2O. So methylene migrate, you have cation at the ring. During the transition, you have ring expansion. 6-member ring becomes 7-member with cation. If you redraw nicely, you can see clearly cation is there. Then OH minus attack, you have enol there. Then the enol converted into ketone by hetoenol tautomerism. End up with final product. The concept you outline here is in ring system, Beckmann rearrangement expand the ring. Then the next example, You have hydroxylamine. One side you have methyl, another side you have chiral carbon with hydrogen, methyl and phenyl. You are using the tosyl chloride and acidic hydrolysis. You should find what will be the final product. Here oxime is there, tosyl chloride you are using, chances of Beckmann rearrangement. But interesting case is chiral carbon. What will happen to chiral carbon is the real question. Here configuration of chiral carbon won't change, that we have seen already. It's a concerted mechanism. First step will be attack of tosyl chloride. Tosyl chloride makes oxygen as the good leaving group. Here the leaving is assisted by the trans group. Trans group is the chiral carbon. Since the mechanism is concerted, chiral carbon move, TSO eliminated, you have cation there. Then the cation attacked by H2O, that is OH minus. You form enol there. Then the enol converted into ketone by tautomerism. End up with amide there. Here the interesting thing is chiral carbon don't change its configuration, stay as it is. The concept you have to learn here is, since the Beckmann rearrangement has the possibility of concerted mechanism, chiral carbon don't change its configuration. Then the next example, here you have benzene, it is an aniline with amide side chain. You have hydroxylamine at the terminal, the concentrated sulfuric acid you are using, then phenyl ketone, titanium tetrachloride and zinc. You should find what will be the final product. Here typically the organic conversion, but Beckmann rearrangement is the middle step. First step is Beckmann rearrangement. As it attacks the OH, you have oxime to H2O elimination. Here trans group migrates. Since the stereochemistry is not specified, hydrogen is the electron denser group. It migrates, form the cyanide there. Since hydrogen is the only migrating group, hence it becomes Beckmann elimination reaction. Because carbonyl cannot migrate, cyanide formation is there. Then there is a chances of cyclization, ring closer by changes of electron. You have new 5-member ring. Then to gain the aromaticity, hydrogen loses. You have benzene with side chain, amine and carbonyl. You are doing acid hydrolysis, which converts into diketone. Then you are using phenyl ketone with Beckmann reagent, which is titanium tetrachloride and zinc. It form coupling reaction, form the alkene. The whole organic conversion dictated by Beckmann elimination and Beckmann reaction. The concept you have to learn here is Beckmann rearrangement can be a part of organic conversion reaction. Then the next reaction, you have benzene fused with 5-member ring side chain alcohol. You are using NOCl in pyridine, light and sulfuric acid. You should find what will be the final product. Here the reaction is organic synthesis. First step NOCl and alcohol group. So you might realize it's a Barton reaction. Barton reaction is the hydrogen transfer reaction. Form oxime. First step will be hydrogen and NO exchange. It form oxime possibility through tautomerism. Oxime form. Then you are using the acid mean chances of Beckmann rearrangement. So oxime gain the hydrogen. Then acid attacks the oxime. H2O elimination. Trans group migrates. Ring expansion happen. Ring expansion happen. Hetoenol tautomerism occur. You end up with final product. Here you should find final product without the mechanism. That is the only way to write the final product in very quick and efficient way. So organic synthesis reaction should find the product quickly and identify the possible products. Then the next reaction, you have bicyclic compound with hydroxylamine, two methyl group at the bridges and one methyl group at another bridge. You are using the sulfuric acid. You should find what will be the final product. Here oxime is the acid you are using. So Beckmann rearrangement. First step will be attack of acid on alcohol. H2O elimination is possible. So trans groups would migrate for H2O elimination. Since the intermediate is the stable cation, Beckmann elimination happen. So cyanide form with cation. Cation is the tertiary cation, very stable. Beckmann elimination is the only possibility. Since the ring also rigid, cation also stable, only possibility is Beckmann elimination. If you redraw nicely, you have bicyclic compound to monocyclic compound with cation. Then the cation has to be quad. So hydrogen migrates, you have alkene formation. This kind of examples we seen already, but different perspective is given here. Then the next example, here you have fused system, 6-member ring and 5-member ring with alkene. Side chain you have ketone. Methyl and hydrogen are trans to each other. You are using hydroxylamine and hydrochloride and aromatic chloride with sulfur leaving group with pyridine. You are heating it up with water. You should find what will be the final product. Here chances of Beckmann rearrangement because you have ketone, hydroxylamine you are using mean the formation of hydroxylamine, but you are using aromatic sulfoxy compound. Technically it's a tosyl system or tosyl derivative, so it form N-tosyl system. It's a very good leaving group. So chances of Beckmann rearrangement. So trans group migrates. You have cation near the alcohol. Trans group is the ring there. The fused ring moves. You have cation at the carbon. If you read down nicely, cation near the nitrogen. Then water attacks. You have the alcohol there. The alcohol is the enol. It converted into ketone there. So the final product is rearranged amide. Here you might have noticed the tosylate form away from the ring because of steric effect. The concept you have to learn here is whenever you form oxime, always analyze the possibility of hydroxylamine because the reaction is controlled by the stereochemistry. Then the next reaction, you have decline, alcohol and hydroxylamine in the nearby carbon. You are using the HCl. You should find what will be the final product. Here you have hydroxylamine acid you are using. So the chances of Beckmann rearrangement, but there is a chances of forming stable cation. So what really happened? Tertiary cation has the possibility mean Beckmann elimination. First step will be oxime hydroxyl group attacked by H plus H2O elimination. H2O elimination by the ring opening because stable cation formation. The cation formed near the alcohol. It considers the ketone there because alcohol can leave the hydrogen, form the double bond, form the ketone. Clearly, the starting material and products are totally different because of Beckmann elimination. The concept you have to learn here is stable cation promote the Beckmann elimination instead of Beckmann rearrangement. Then the next example. Here you have fused system, 6-member and 4-member ring fused together. You are having hydroxylamine at the 4-member ring. You are using the sulfuric acid. You should find what will be the final product. Here you are having hydroxylamine and you are using the acid. So Beckmann rearrangement. First step will be acid attacks on hydroxyl group form the H2O. Since the ring is very strandful, ring try to open and assist the H2O elimination. Even though no trans group is there, due to the ring strand, ring open itself promote the rearrangement. Ring open mean H2O eliminate. You have cation on the carbon. If you read it nicely, you can visibly see 4-member ring will become 5-member ring with the cation formation. Then the cation attacked by OH minus. OH minus attacks. You have alcohol. Alcohol is the enol. It can convert to ketone by tautomerism. So the final product is ring expanded amide. The concept you have to learn here is ring strand can assist the Beckmann rearrangement. Then the final example, you have fused system, 4 member and 5 member ring, 2 methyl groups and 1 hydroxylamine. You are using the PCl5. You should find what will be the final product. Here PCl5 we are using. PCl5 can abstract the oxygen. For simplicity, I written as H plus. OH attacked by H plus form H2O. H2O is the leaving group. Trans assistance is required, but trans assistance leads to the cation formation. The cation is the stable cation, so Beckmann elimination is possible. So instead of amide formation, you end up with cyanide. The cation has to be quenched. It quenched by chloride, end up with cyanide and halide. The concept you have to learn here is whenever there is a stable cation formation, Beckmann elimination dominates instead of Beckmann rearrangement. Let us summarize what we seen. Beckmann rearrangement is conversion oxime into amide through the migration of trans group. Here catalyst can be Lewis acid or Bronsted acid. The migrating ability decided by the stereochemistry. If stereochemistry is specified, trans group migrates. If stereochemistry is not specified, cation stabilizing group migrates. Since hydrogen is electron richer, hydrogen migrates first, then phenyl, then tertiary, secondary and primary. Basically, this order is cation stability order, or you can say the species stabilize the cation. The more important thing is if there is a stable cation formation, definitely Beckmann elimination instead of Beckmann rearrangement.